Thank you very much for the introduction. I didn't plan this with Peter, I promise you, but I have a similar topic with a slightly different focus. Okay, I concentrate more on the calibration and the measurement side, and Peter concentrated more on the planning, on the programming side. It was a coincidence, but a happy one, I'd like to say. So what I'd like to talk about today is just a bit of background, a bit of the motivation for CanFD. I think this is known, so I'll go through it quite quickly. Some main changes. Some of the other changes, because CanFD is more like a CAN 2+ standard. Again, I'm going to talk about XCP, introduce XCP, and actually explain what changes have actually been done to the XCP standard because of CanFD. A little bit about the effects on the data download. This is very much like the flashing type stuff. And what I'm going to do is talk a little bit more about the effect of CanFD on measure performance. And I'm going to try and do it with some real-world examples, because I'm an engineer, I'm not a software developer, and I like to know actually what does that mean in terms of number of signals I can measure or number of bytes I can measure. And then we'll do some conclusions. Okay, I think the motivation for CanFD is relatively clear. It needs to be faster, and the actual the message overhead compared to the actual data payload is relatively high with CAN, so it means the efficiency isn't that high. So we want to make it faster, and we want to increase the payload. Now then, I also have an animation, maybe not quite as slick as Peter's, but let's do it anyway, where again, it shows what are the main changes of CanFD. The first change is in the data phase, where we actually can send the data faster, so we can actually increase the actual rate we send the data at. Okay, and the second change is then to have the ability, we don't have to do this, but the ability then to increase the amount of payload that we have from 8 to 64 bytes. Is that better? Oh, gosh. Okay. And what this means then for the effective payloads, what I've done is just plotted this out again. I think many people have seen this graph. We just plot this out against the data, the actual the FD part of the data phase, and that which you show that the net bit rate with the different payloads. And of course, with 64 bytes, then of course we send a lot more data. Just a little bit, again, just going through the differences in the CAN frame, is just then to keep the presentation complete. What we see is the remote transmission request is actually then set to a dominant, and this means that there are no remote frames with CanFD. The extended data length is actually the signifier for CanFD. This is recessive. In the normal CAN frames, this dominant. This is the reason why you can't really mix normal CAN and CanFD on the same node, because when a normal CAN node sees a CanFD, it sees this frame and says, "Ooh, error," throws an error on the bus. The bit data rate switch is the actual the switch that actually says, "Okay, change the rate now," and I'll come back to the error state indicator in a minute. Okay, so what we've done, the actual data length code, we've used the same 4 bits as before, whereas in legacy CAN, when you had a 1 bit in the a 1 in the data length code 3 bit, it meant that it was just 8 bytes. What we've done now, we've actually used then all the codes then to extend the data frames. This is why you only have this pattern here. So, for example, you can't have a data length code of 35. It doesn't work. We only have these 8 possibilities. And also then, because of the longer payloads, then we've actually increased the checksum routines to enable to actually handle these. There's just a couple of other changes in CanFD. Although they're mainly related to the data rate and the payload, there are some other changes which makes it more like a 2+ specification. So some changes not directly related to the data rate and the data length. So one of them is the error state indicator. The error state indicator is actually there to try and help you debug buses which actually throw error frames, because then we can identify which frames are actually which nodes are actually sending error frames by indicating with the bit here. And the second change is in the checksum part there is a fixed stuff pattern, so a fixed stuff bit pattern, whereas before they would follow a pattern where you had 5 consecutive frames and bits, then it would, if they were all the same, it would send an opposite one. Only in the CRC there is a standard pattern where we send a first stuff bit, which is then opposite to the previous bit, and then every fifth then is then a fixed bit. That means we know how many bits there are in that CRC frame. Okay. Then, Peter introduced the XCP standard. I'll also talk a little bit about the XCP standard. What it is it's CP stands for Calibration Protocol, and XCP means it can actually run on any bus system. It was a successor to CCP for CAN Calibration Protocol. So XCP can run on Ethernet or FlexArray, but we predominantly see it on CAN because there are more CAN buses than there are FlexArray or Ethernet buses. Quite simple. And it's actually the main tool used by calibrators. So these are the guys who sit in the car and actually do the measurement and calibration. The latest standard for XCP was released in June this year, and it was the 1.2 standard. The XCP standard's run by the ASAM committee, and this standard actually supports CAN-FD. And so I'll just talk about what changes there are actually in the standard directly that actually relate to the CAN-FD. Firstly, we have some additional information in the A2L file. So this is the A2L file has what we call an AML, which is an A2L meta language. And this is the part that tells the calibration tool, hey, how am I going to talk to the ECU? And in here, then we have some new parameters, which keywords that we need then to tell the tool that we've got CAN-FD frames and what information it then needs to send down to the controller. I don't intend to go through all these. This is I've just put it on here for reference. But the main ones being the max DLC, so what's my size, and then the FD part, so the baud rate. Then the second part is a little bit more complicated. The second part then is the XCP actually introduced a raster check calculation for dynamic DACs. Okay, DACs are called data acquisition unit. Data acquisition. It's actually the method we use to measure data out of the ECU. Okay, and there are two types. One of them is called static, where the actual the CAN ID is directly related to an event. So we measure at 10 milliseconds or 100 milliseconds. All the 10 millisecond measurements happen with one CAN ID, and all the 100 milliseconds with another CAN ID. It means we can work out how full the rasters are. The other one is called dynamic DACs. With the dynamic DACs, it's a bit more complicated. It's free. Okay, any event can go to any CAN ID for the DACs CAN IDs. That means we can't predict how full the rasters are. We can't tell the user, hey, you've overfilled your rasters, or you've selected too many measure variables, and he doesn't know until he starts measuring, and then the ECU says, oh, I've got a problem, and stops measuring, and then he misses his test. Okay, and what the XCP introduced was a method to actually do this raster calculation. Part of it is a bus load calculation. And of course, because of the CAN-FD affects the data transfer rates, we have to modify this bus load calculation to take into effect CAN-FD. And again, I don't want to go too much into it. It's more to tell you that it's there. But basically what we do, we have to normalize the bus rate calculation with the CAN-FD data rate. And what we've done is specified then the data length frames. We do a normalization to find out how many bits of CAN basically are sent for every event. And then what we do, we add it for each event and then add this together all events. Again, I don't want to go into this. It's normal for information that this is there. This change has come in, and it's come in because of CAN-FD. It's just to make you aware of it. Okay. So the data download. A lot of information has been published on the data download, and Peter also talked about it. This is just a theoretical study. What I've done is just to look at a comparison between legacy CAN and all the different CAN, CAN-FD configurations. What I've done is I've assumed that I'm actually downloading 500 kilobytes of data. with a 1,000 kilobyte per second arbitration speed, a block size of 255 kilobytes. The block size means how many messages I can send before I get acknowledged then from the ECU. It means I reduce the amount of traffic. And the ST-min is a separation between the CAN messages. I set that to 0. What I find is, so this is basically where we are today. So this would take 8 seconds in this theoretical. And as I increase the flexible data rate, then you see that the rate comes down. So, for example, if I set this to then 5 seconds here, I go from 8 to about 3 seconds. It's almost not quite a third, 2.5 times improvement. And again, with 64 bytes, significantly more improvement, especially when I get to 5 megabytes. I'm down from 8 seconds to 1 second for downloading the data. Okay, what I want to do is concentrate a little bit more on the measurement side, because when I looked at what has been published and what has been written about CanFD, a lot has been talked about data download, a lot has been talked about flash times, and not much has been talked about measure performance. And when I started to analyze it, I understood why. The problem is, the measure performance is complicated, and it's complicated because we have lots of possible combinations. We have combinations of different measure rates, we have combinations of how much data we want to measure, and actually doing an analysis of this was relatively complicated. So what I wanted to do is I just compared the 8 and the 64 bytes. The 8-byte system because it's the easiest change, the 64-byte system because it offers the best transfer performance, and also because we reduce the risk of data consistency problems. What can happen is when you're measuring data with XCP, the ECU sends a big chunk of data, it gets put on the CAN bus, and then some more data is sent by the ECU before all the information is then put on the CAN bus, and then we have to try and manage that data, and we can improve that using 64-byte. What I've done for the analysis then, to try and keep the analysis easy, I've said we have an arbitration rate of 100 kilobits per second, and what I've done is I only measure in 10 milliseconds. So all my calculations are just done with one raster, 10 millisecond raster. This makes the actual analysis a lot easier. So, okay. This will make sense in a minute when I put the rest of the graph on there. The first one I wanted to do is, one of the typical limits we have is the user says, or the ECU manufacturer says, we only want to have a certain, the XCP can only take up a certain bandwidth on our bus. So, for example, typical is 30%. So what happens is, if we want to maintain that 30% bus limit while changing to CanFD, okay? And now it makes sense. What I've done is, if I have a legacy CAN and I'm measuring at 10 millisecond raster with 30%, I can actually send 184 bytes of data every 10 milliseconds. So for example, if that's a 2-byte data, then that's about 92 messages. So I can read 92 CAN messages every 10 milliseconds. Now, I've plotted this out as a baseline line here. Of course, it doesn't make any sense because, of course, you can't have a legacy CAN with 10 megabit data rate, but it's just then to see the comparison. If I move to just to have the 8 bytes, and for example, I go to 5 megabit per second, I'm actually going from 184 bytes to 480 bytes. I can send significantly more data. I'm now receiving, instead of 92 messages, I'm now receiving 240 messages. Okay, I could read a lot more data out the ECU. Increase that to 64 bytes, and I'm now up to 1,216 bytes. Significantly improved performance. That means maintaining the same CAN bus load, I can read a lot more data out the ECU. What about if I turn it round? Okay, that's the only... I know why that is, but it doesn't matter. If I turn that round, let's say the limitation is actually in the ECU, it's not from the bus load. Let's say I maintain my measure performance. What effect then does that have on the bus load? So what impact does my XCP actually have on the bus load? And if I look at this, what you see then, again, I've just plotted the legacy CAN out just as a baseline. Again, if I concentrate at 5 megabits per second, I reduce, with the 8 bytes, I reduce the bus load from 30% to 12%. So just increasing the flexible data rate means I have a lot less impact on the bus using my XCP measurement. Again, to 64-byte, I'm down to 4.5%. This means actually you could start thinking about using doing XCP on normal vehicle CAN, where before maybe it wouldn't be possible, you'd have to have an extra CAN line in there. That's one possible application of this. Okay. The third one I did, the third analysis I did, is to say, okay, let's say I have a limitation at the moment, how fast I can actually send data out. Could I use CANFD to actually measure faster out of the ECU? And measuring faster out of the ECU, maybe I can look at some more use cases. So what I've done is I've done some analysis saying, if I wanted to send 64 bytes of data in a half a millisecond raster or a 0.25 millisecond raster, so every 0.55 milliseconds I want to send 64 bytes data, and every 0.25 data. So if I start off here with the 8 bytes, at the moment, if I wanted to send 64 bytes, we can today, at half a millisecond, I have a bus load of 200%. It's not possible. Okay, so I cannot send this amount of data this fast. If I start then increasing the flexible data rate, it's possible with the 8 bytes at 5 megabit per second. With 64 bytes, I'm actually down to about 30% bus load. This becomes feasible. I can now actually then start to use this to measure faster out of my ECU. If I look at 0.25 milliseconds and even faster, again, the bus loads are higher, but again, it is possible to do this with the 64 byte. With the 8 byte, it doesn't really make it, we can't do it. So if we have 8 byte payloads, it's always over 100%. With 64 byte payloads, this is possible. What this means, it's possible to maybe open up new applications for using XCP on CAN, whereas otherwise you'd have to use Ethernet or FlexRay before. An example is for electric motors or hybrids where you want to actually measure data faster than you do today. Okay, so wrap it up. So what I've done is I've just told you a little bit about the CAN format, and I've also tried to explain what the actual changes are for the XCP 1.2 related to CANFD. Okay, download times, flash times. Okay, we've seen that many times before. These can be significantly improved. And what I wanted to do was to really try to show you that actually, yes, the flash times are improved, but you can also really improve your measure times, and we can actually have some significant measure performance, or we can reduce the impact of your measurement on your CAN bus. And maybe, because we can measure faster, we can open up new use cases that weren't possibly possible with XCP on CAN. So, that was it.
Thank you.